So our second skill in our learning unit here on nuclear chemistry deals with reaction rates and deals with what we call first order processes. And so these first order reactions are what happen with nuclear decay. And this is going to be a great preview and intro into our next learning unit, which is going to be on kinetics. So just a little bit of background on understanding rate and what we think about with rate. Rate is really a change in some variable per unit time, right? We can typically think of rate in terms of speed, right? Which is really the change in a position, maybe it's of a car or of a person, over a change in time. And that gives us units of, say, meters per second or miles per hour. So we can think about rate for chemical processes similarly, but now the change in the quantity is going to be the amount of a material, and it's still going to be per unit time. So let's take just a little decay process here. This is something that we've learned about in our last skill here. For example, this is strontium-90 undergoing decay by eliminating beta particles and generating yttrium. Just as a little preview here, remember we talked about being careful if you've got negatives here, and that's why we actually increase the number of protons when we have a beta emission. And look here, that's because when we add these two together, that's how we have that 38. So if we knew that this was a beta emitter, that meant we actually increased the number of protons in that element. What we're going to talk about here now is something called half-life, and you've probably heard of this. Half-life is basically the amount of time it takes for half of that sample to decay or go away. So if we started out, for example, with 10 grams of this strontium-90, if the half-life is just under 30 years, we would be left with 5 grams after that 28.8 years. If we wanted to let another 28.8 years go by, another half would disappear. It's not that 5 grams now continues to go away each time, it's half of the half that's left. So now we're left with 2.5 there. And then we're left with 1.25 and so forth. So we're going to do a problem in class that has us think about this concept of counting half-lives, and we're going to go through and use an equation today that allows us to think about calculations involving half-lives. So when we think about this rate is going to incorporate an important constant that we're going to call the rate constant. It's a lowercase k, often an italicized k, and we'll call this little k. And that's going to contrast to big K, or a capital letter K, that we'll see in the learning unit after that, which is on equilibrium. So just a little preview, we're going to kind of see these chapters or these units build on one another. So nuclear decay is what we call a first order process. So what does first order mean? That means it doesn't depend on the amount that's there. So imagine we're sitting there with this 10-gram sample of strontium. It's going to decay at the same rate, whether there's 10 grams, 10 milligrams, or 10 kilograms. That rate of decay is not going to change if I change the amount that I have. And that's not necessarily the case with enzyme reactions or chemical catalysts. So, but this little k is going to depend on the identity of that isotope that's kind of being decayed. And so what we can see here is that this blue line represents something that's decaying more quickly, and we can see that that has a half-life that's faster than, say, this line right here, which has a much longer half-life. Okay? So 2 equations that we see in this skill. The only 2 equations that we're going to use to do calculations. This first equation allows us to relate the half-life with the rate constant. Most often you're going to use this equation because a problem will give you the half-life, and you're just going to use this very simple equation to solve for K and calculate the rate constant. Well, why do you need the rate constant? This is sort of the big money equation for this chapter. This is what we call the rate law for a first order process. There's 4 variables to this equation, and you're always going to be solving for one of them. This little scripty n just represents quantity, okay? That little 0 tells us the quantity when you start. So again, this can be a quantity in terms of grams or milligrams. It can be activity units. It doesn't matter what the unit is. It just represents the amount that you start with. So this equation basically tells us that there's a ratio between the amount that you start with, the amount that you have after a certain amount of time has passed, the amount of time that has passed, and then the rate constant. Usually you're not solving for the rate constant, but you're either going to solve for one of three quantities. Those three quantities are: how much did you start with? How much do you have right now? How much time has passed? So I'm going to say that again. This equation is going to be one that you're generally going to be solving for one of the non-rate constant variables. You're either going to be solving for how much did you start with, how much do you have after a certain amount of time, or how much time has passed. And that how much time has passed question has a lot to do with carbon dating and things like that. So I'll show you that at the very end here, but let's just go through a sample problem here. Let's look at and imagine cobalt-60 that has a half-life of 5.3 years. We want to know how much of a 1 milligram sample is going to be left after a 25-year period. So remember these two equations that we have. The half-life is equal to 0.693 over K. So this half-life is what was given to us, right? The half-life is 5.3 years. So we're going to put that in here, and we're going to solve for our rate constant. So this again is a piece of information that we're interested in because we're going to use that to put into our second equation. So the second equation tells us the natural log of what we start with over what we have at a certain time is going to be equal to K, the rate constant, times T. So highlighting, we are going to use this equation to generate our K, which we're going to use in this equation. So now let's just kind of highlight the pieces of information that we have here. We start with 1 milligram of sample, so that's what we're going and putting in there. 25 years has passed, so that's going to go in here. And again, the rate constant we're going to get from the half-life. And then what we're interested in solving for is this last piece here, right? We're interested in solving for how much is left after a certain amount of time. Okay, we want to know how much is left. So as we practice some problems like this in class, we'll see there's lots of different ways to ask these questions. And a couple of things that are set up very easy in this problem that might be different later on. We have to watch our units. Here the half-life is given in years, and we're talking about years here. So we have to make sure that things are in the right units. So this one is pretty straightforward because everything is given to us in easy to use units. So let's go ahead and solve for our K. It's 0.693 over T1/2. So K is going to be equal to 0.1308 reciprocal years. Rate constants for these first order processes are always going to have units of reciprocal time. Now let's go ahead and put all of our pieces in over here. The ln of what we start with, which is 1 milligram. I'm not going to put units in. We don't need to worry about units here because it's just going to be our answer in the same units of milligrams. We're going to solve for n sub t, how much is left. We've got 0.1308 reciprocal years times 25 years has passed. So you'll notice here, again, this is why it's important that we match these units. Problem might have an added level of difficulty if these aren't the same units. So we do want to put those units in to make sure that we're matching that. Okay, we're going to have ln of 1 over n sub t. It's going to be equal to 0.130825. Keep significant digits until we're ready to round at the end. But this is where this problem becomes a little bit of an algebraic challenge, making sure that we know how to solve these problems when one of the unknowns is part of an ln relationship. So remember, if we take e to the both sides, right? That's going to allow us to get whatever was the ln of that. So we're going to get 1 over n sub t. And then when we take e to whatever that number is at 0.130825, that's going to end up giving us, oops, and I actually didn't put the right value in here. I didn't multiply those together. This is 3.2689. My apologies. 3.2689. 3.2689. There we go. So when you take e to the 3.2689 in your calculator, you're going to get 26.281. So it's very important that you understand how to do that algebra, how to separate out that n sub t from that ln equation. Now this last algebraic step is pretty straightforward. 1 over n sub t equals 26.281 if you take 1 over both sides of that equation. So again, take 1 over this and then 1 over that. That's going to give us our final answer. N sub t here is going to be equal to 0.038, and I'm going to put the units of milligrams back in. Now I just want to highlight a good thing to do is kind of predict what you think that answer might be. See if you can follow this logic for a minute. If I start with 1 milligram, after 1 half-life, I'm going to have a half a milligram left. If I go through another half-life, I'm going to have 0.25 milligrams left. And I think you see sort of where this is going. 0.125 is going to be 3 half-lives. 0.0625 is going to be 4 half-lives. And if I go through one more half-life, this is going to be 0.03125. So why did I bother going through that? Well, let's look at this. If 1 half-life is 5.3 years, after 25 years, I haven't fully gone through 5 half-lives, but somewhere between 4 and 5 half-lives. So I should be then having an answer that's somewhere between these two answers, okay? And I can see that 0.038 milligrams is between these two. Okay, so we're going to talk about that more in class, but this is a great, just simple example to practice these two equations that are essential to this learning unit. And just kind of like a last little piece here to highlight the theory behind how radio dating works, how carbon dating works. If we look at what's going on here, this is how we generate this trace isotope of carbon, carbon-14. That's what we call carbon dating. It's looking at the incorporation of this radioactive carbon in living things. So this is how this happens. You actually have atmospheric bombarding of nitrogen to give us this carbon. So we'll go through that chemistry. But basically what happens is anything that grows and it takes in carbon from the atmosphere, it's going to take in regular old carbon, a little bit of carbon-13, and then trace amounts of carbon-14. So what happens is any living organism is going to bring in that carbon-14. And then when the organism dies, basically you have a ticking clock, if you will, of the decay of a constant amount of carbon-14. That's going to give us a ratio of this radioactive carbon-14 to the regular carbon-14. So as this carbon-14 begins to tick away, the more that's ticked away, the longer it's been since that organism was alive, and that ratio will allow us to then determine the age of any living organism. Okay, so we'll practice some problems like that in class.